Here's another example. For the mixing problem described in example 1, assume now that the brine leaves the tank at a rate of 5 liters per minute instead of 6 liters per minute, with all else being the same. Determine the concentration of salt in the tank as a function of time. So the only difference here is that we have 5 liters per minute instead of 6. So let's start out by defining our x of t. X of t is the amount of salt in the tank at time t. So now the thing that is different here is that the volume in the tank will not be constant. So previously, we had that the volume was a constant. Namely that 1,000 liters. But now we see that there's a net inflow of 1 liter per minute, right? 6 liters going in, 5 liters coming out. That means 1 extra liter per minute is accumulating in this tank. So what we need to do, instead of thinking of V as a constant, we need to think of V as a function of T, right? And the volume at time t will be a linear function. We'll have an initial volume, V naught, and then we can think of this as a net flow rate times t. So in this particular case, V of t equals 1,000 plus 6 liters coming in, 5 liters coming out. So 6 minus 5 times t. And so our final V of t is 1,000 plus 1 times t, or just 1,000 plus t. So that will change things a little bit, that it's no longer constant. Okay, so now we're going to write down our differential equation, which is dx dt equals, and now we're going to write down the same thing as before. It's going to be the input flow rate times the input concentration minus the output flow rate times the output concentration. Okay, and let's not worry about units because we know the units check out. So the input flow rate is still 6. So we have 6 times the input concentration is 0.1. And then we're subtracting 5 times, right, the output flow rate times the output concentration. And we know that concentration, remember from the previous concentration. Previous example, concentration is the amount over volume. And so for the output concentration, the amount is x of t, and the volume we just established is 1000 plus t. So now our differential equation dx dt is 0.6 minus 5 over 1000 plus t times x. Now let's take a moment and think about what type of differential equation this is. So what we have here is a linear differential equation. So in order to see that and to solve that, we need to write the equation in standard form, right? So let's do that here. Write it in standard form. We're almost there. We already have the leading coefficient of 1, but we need to get the x on the other side. So the standard form of our differential equation is as follows. It's dx over dt, and then we bring the x to the other side, and that's going to be plus 5 over 1000 plus t times x, and that equals 0.06, or sorry, 0.6. So from that standard form, we then see that our P of t is 5 over 1000 plus t, and our Q of t is 0.6. So the second step is we want to find the integrating factor, mu of t, which is e to the power, and then the integral of p of t dt. Right, and what we get there is that mu of t is e to the power integral of 5 over 1000 plus t dt. And this integral, we can do a substitution, u equals 1000 plus t, and so you'll get 1 over u, and so you see that the antiderivative is an ln, and I'm going to do that over here. So double check that you can find the antiderivative of this. So we have 5 times ln of the absolute value of 1000 plus t. And then what we're going to do is bring that 5 inside the ln, so that will be a power of 5. And then the e and the ln cancel, so this is going to be 1000 plus t to the power 5. And we're not going to worry about the absolute values here for the integrating factor. So we'll see that this one works without having to worry about the absolute values. And that's because we're looking at positive times of t, and so the absolute value of 1000 plus t is just 1000 plus t. Okay, so the third step that we're taking here is to actually find the solution using that formula. And so we just need to replace y of x by x of t. So x of t is 1 over mu of t, and then times, in brackets, the antiderivative of mu of t times q of t dt plus a constant of integration. So let's do that. So what we get here is that x of t is 1 over mu of t, so that's 1 over 1000 plus t to the power of 5 times antiderivative of 1000 plus t to the power of 5 times 0.6 dt plus c. And now when we're integrating this, we can again use the substitution u equals 1000 plus t, and then this is basically u to the power of 5 du, because du equals dt in this case. And so the antiderivative of this will then be add 1 to the power and divide by that new power. So what we get is 1 over 1000 plus t to the power of 5 times, and then this integral is going to be 0.6, a constant multiple, times 1000 plus t to the power 6 over 6, and then plus c. And then we can multiply this out, so distribute this, and what we get is that x of t equals, and you see the 5 cancels with the 6 here, and there's 1 power. 0.6 divided by 6 gives you 0.1. So we get 0.1 times 1000 plus t, and then plus c over 1000 plus t to the power of 5, right? That's this factor times that term c. So that's our solution for x of t. Now to determine c, we need to use our initial condition. So that's our fourth step, is to find C. And what we need to know is that the initial condition is, again, x of 0 equals 0. So initial condition is x of 0 equals 0. So that means t is 0, x equals 0, t and x. And let's plug that into our equation. We get x of 0 equals 0.1 times 1,000 plus 0 plus c over 1,000 plus 0, plus 0 to the power of 5. Right, so okay, so the left-hand side is 0, and then the right-hand side, we get 1,000 times 0, or sorry, that's 1,000 plus 0 is 1,000 times 0.01, that's 100, and then plus c over 1,000 to the power of 5. We bring that 100 to the other side, and then we multiply both sides times 1,000 to the power of 5. And I will not rewrite that. So we get c equals negative 100 times 1,000 to the power of 5. You could simplify that, but I'll leave it like this. So that's our C, and our solution, x of t, that's the amount of salt in the tank, is 0.1 times 1,000 plus t plus c, and that's a negative, so we actually have to make this a negative. So that's minus 100 times 1,000 to the power of 5, or 10 to the power 17, and then divide that by 100, or 1,000 plus t to the power of 5. Okay, so that's one part of our answer here, right? Because we were asked to determine the concentration, and x is the amount of salt. So to determine the concentration is amount over volume. So we have to go back, and to get our final answer for the concentration, let's keep in mind that concentration equals the amount that was x of t divided by the volume, so that's v of t. And when we do that, we get 0.1 times 1,000 plus t, and we divide that by v of t, Let me use a different color there to make that a little pop out a little bit more. So, oops. V of t, right? V of t was 1000 plus t. And then we also have to take the next term and divide that by 1000 plus t. So we subtract, then it's 100 times 1000 to the power 5 divided by 1000 plus t to the power 5. And then we're going to divide that by 1000 plus t. And let's clean that up a little bit, because 1000 plus t and 1000 plus t, that cancels. So our concentration, the first part is 0.1 minus, and if we divide 1000 plus t to the power 5 in the denominator by 1000 plus t, that gives us a power 6. So this is minus 100 times 1000 to the power 5 over 1000 plus t to the power 6. And that is our concentration as a function of time.